Module 6 is the final module of this course and addresses the last two competencies to be considered. Describe electromagnetic radiation and its interaction with matter. Describe the basic structure of the atom and the nucleus. The first of these are addressed in Chapter 18 in the development of our understanding of the structure of the atom, which then addresses part of the second competency. X-rays were discovered as an outgrowth of the study of cathode rays, which turned out to be electrons, one component of the atomic structure. X-rays have since been used in a variety of areas because of the penetrating ability due to their high energy. The study of radioactivity showed that there were three different types of particles given off by this process. This further provided evidence for the structure of the atom. One of these turned out to be a high-energy form of electromagnetic radiation, gamma rays. These are some of the highest energy electromagnetic radiation we know of today. Their production is related to nuclear structure as explained in a later chapter. Further studies using another of the particles given off during natural radioactivity, alpha particles, help to define the size and nature of the atomic nucleus. Scattering of these alpha particles off gold foil and noting the angle of scatter of the detected alpha particles demonstrated the small, dense nature of the atomic nucleus. The discovery of the relationship of different sets of spectral lines to specific atoms further led to the understanding of atomic structure, leading to what today is known as the Bohr model of the atom. Though this has since been replaced by better models as more work was done, it was the first step to help explain the formation of spectral lines, at least those of the hydrogen atom. Absorption lines were explained as a result of an electron moving from one allowed orbital to a higher one, the upward movement the result of removing a specific amount of light energy from the incoming light to move to that higher orbital, while emission lines were formed when discrete amounts of light energy were released by the electron in a higher orbital to move down to a lower one. In each case, the amount of energy was the same, as described by the equation E equals hf, where E is the energy of the photon either captured from the incoming light or released from the downward transition, F is the frequency of the photon captured or released, and H is known as Planck's constant. Thus, the particle nature of light allows us to go back to the first competency addressed in this module, describe electromagnetic radiation and its interaction with matter. Quantum mechanics is offered as a better way to model atoms and the electron configurations around them. Success came with the discovery that just as light has a particle and wave nature, matter does as well. Electrons treated as waves help to explain why, for example, there were only a limited number of locations outside the nucleus where an electron can be stable, have an apparent orbit. Configurations of such electrons around the nucleus help to explain some of the characteristics of the periodic table, first introduced in this chapter. Further understanding of the electron configurations came with the Heisenberg uncertainty principle, limiting our knowledge of the exact location and momentum, for example, of the electron, moving us away from specific stable orbits to what are referred to as probability densities, the probable location of those electrons within the atom. Chapter 19 is more involved with the nucleus of the atom, giving a history of the discovery of the parts of the nucleus, the neutron and the proton. From the discovery of these particles, the nature of different types of nuclei within the same element can be explained. Isotopes are different versions of the same atom, different by what is called their atomic weight, essentially different numbers of neutrons complementing a fixed number of protons. The proton count, and by extension the electron count of a neutrally charged atom, determine the type of the atom, the element. The neutron count can be related to how stable or unstable a particular type of atom is. Radioactive decay results when an atom is not stable, generally because its nucleus has too many or too few neutrons compared to the protons in its makeup. By ejecting particles from the nucleus, one of the three types covered in Chapter 18, some sort of stability is achieved. In this way, different elements can be created from different starting unstable nuclei. Though the goal of unstable nuclei to become stable can travel different paths by emitting one of the three different types of radioactive particles, the rate at which that happens is different for each radioactive nucleus. Some can do so in seconds or less. Some take millions or billions of years to do so. This helps to account for different abundances of different elements of the periodic table. And even though this process is random, it is possible to track for each a time period over which half of that initial sample will decay. This is known as the half-life of the radioactive nucleus, and all nuclei follow the same process of radioactive decay using this concept of half-life. Nuclear reactions are another outcome of the study of the nuclei of atoms. Not only can they decay from one atomic species to another, but it's possible to force a situation by bombarding the nucleus with alpha particles or neutrons in order to form a different atomic species. Eventually, this led to the discovery of nuclear fission, which can be used today for nuclear power generation or, if uncontrolled, nuclear weapons. Quite a bit is covered on the use of nuclear reactions, primarily using isotopes of uranium, in the production of energy via nuclear fission power plants. The generation of energy by fission has its upsides and downsides. Both are covered in this chapter. The holy grail of nuclear energy is nuclear fusion. Only recently has nuclear fusion been done anywhere close to what the hope is, creating more energy than it takes to make it work. This chapter goes into some details that are needed to make fusion a viable energy production process. To this date, its only use has been in weaponry, but in the future, the hope is that, done properly, it can replace our dependence on fossil fuels and be a clean energy alternative. So this last module moves us into what is referred to as modern physics. Some of what is covered in the past modules, especially evoking things like conservation of energy and conservation of mass, still continue as we move from traditional physics topics to those covered in modern physics. This further illustrates something said earlier on in this course. We don't leave the tools learned in one chapter behind, but bring them forward to be used in new applications.